Hello and welcome to Teqtron's overview of our cloud API solution powered by Apigee, Kubernetes, and Istio. My name is Jeff. I'm the Director of Sales here at Teqtron, and very shortly I'll be turning the presentation over to my colleague Abhinandan, who is one of our technical experts and will walk you through the details of the solution we have created. As we know, we live in a multi-cloud world where the use of public cloud is the new normal. In fact, IWC predicts that 93% of organizations are using services from multiple cloud providers, and 15 of them are using them from more than 10 providers. At the same time, the evolution of an on-premise IT environment, team, and methodologies is driving more than ever before the adoption of public cloud and the need to access the best tools, technologies, and platforms to give businesses speed and scale. But change isn't easy. You are often forced to choose between your existing IT environment and the public cloud. This can lead to many different solutions, many different problems, and many different environments. Our goal at Teqtron is to help companies with this journey through a guided and validated path. We will be continuously validating many solutions and market claims. There are frequently asked questions like, does the solution work for multi-cluster? Will a hybrid solution work? Will it work for multi-cloud environments? In this video, we will be demonstrating our technical expertise in a multi-cluster deployment use case with GKE. Our mission is to drive your adaptive digital transformation. At this time, I'll turn the presentation over to Abhinandan. Thank you.
Thank you, Jeff. We'll start off by talking about the basis of our solution, the distributed microservices model. With the shift towards digital distribution of data, comes a change in infrastructure that supports the shift. Many companies are looking at a distributed microservices architecture for the future of their applications and data. A major benefit for switching to a microservices model will be scalability, which is the easy scaling of infrastructure to adapt to changes in load for your application. The modular nature of microservices architecture also enables smaller teams, leading to increased effectiveness through a division of labor. This division of labor is reinforced by the language independency of microservices, allowing a company to play to the strengths of their existing team members. In the microservices model, faults are isolated to the service in which they occur, meaning the whole application doesn't have to be affected by an unexpected exception. All of these factors contribute to a general increase in efficiency, meaning shorter development and iteration cycles. There are some weaknesses in a microservices architecture, including a greater overhead cost for databases and servers. However, some of this cost can be offset by the scalable nature of applications built with microservices. Finally, there is an increase in complexity in this model, with many moving parts and webs of communication required to achieve the functionality that companies require. We will be addressing how some of the software we are applying can address this complexity. Companies often spend an enormous amount of effort to hide and protect internal data from external users by configuring and customizing multiple applications. Internal data is most commonly distributed across multiple applications, both in the cloud and on-premise. We have devised a solution that will achieve a scalable, configurable, and sustainable view of internal data. We will have an advanced security model to access multiple systems using APIs. In our solution, external entities do not need to log into multiple application systems, but rather to a single application, which will be made available through web and on mobile devices. We will feature Kubernetes, Istio, and Apigee as the main players in our solution. These technologies will work together to deliver a modern application deployment environment using a distributed microservices infrastructure. Here is a basic overview of the architecture that we have implemented. There's a lot going on here, so let's break it down piece by piece, starting on the left with an HTTP request made by a user to the application frontend. This HTTP request will enter what is called the service mesh, which in this implementation is a network of services that spans multiple clusters, managed by a software called Istio. The service mesh will be a secured environment where services for both internal and external consumption will be hosted. All requests will come into the mesh through a single endpoint, the Ingress Gateway. The gateway will direct information from requests to all of Istio's security and analytics features, as well as all policies set up to manage the mesh. Finally, the request will be directed to a sidecar proxy, which is a proxy DNS endpoint that resides on the same deployment unit as each of the services. We will further discuss this in the Kubernetes portion of the presentation. Finally, the service itself, which can be written in any language, Node.js, Java, Python, will access the data which can reside in any application backend, whether it be on-premise or on cloud. Now that we have a general understanding of the architecture, we can take a deep dive into how each of these technologies are functioning. Kubernetes is the environment in which our containers will be running. It is a container-centric environment that orchestrates computing, networking, and storage infrastructure. Let me start by going over the Kubernetes architecture. The largest unit is a cluster, which is the group of uniform physical or VM instances which together will run the Kubernetes platform. It is responsible for master functions like job scheduling and running the Kubernetes API server. Each individual machine is called a node, which contains the container runtimes, the proxies responsible for port forwarding, and the service that maintains the pod-specific definitions of your deployments. The smallest deployable unit in Kubernetes is a pod, which contains the application containers and defines the storage space and unique network IP that those containers will use. Now we can cover some of the core features of application deployment in Kubernetes. Automatic bin packing allocates resources to containers based on their requirements. Batch execution schedules jobs to maintain Kubernetes objects to redeploy upon failure. Service discovery features set up unique IP addresses for each service, and load balancers manage the traffic to it automatically. Secrets and configuration management allow for secured storage for security certificates, passwords, and other credentials. Storage orchestration automatically mounts storage systems from cloud storage to local systems. Kubernetes also has a versioning system for each application that can handle live updates with no downtime for services. If applications crash, the service is automatically scaled up to avoid downtime. Scaling features in Kubernetes support manual or auto scaling of resources for each service. Istio is a tool that manages the service mesh, which describes the interactions between a large network of microservices. It addresses challenges faced by those who are moving from a monolithic application to a distributed microservices model, specifically managing the complexity of a growing service mesh. You can monitor the performance of services and how that affects the performance of processes and flows as a whole. Traffic control features allow configuration of traffic routing, allowing to establish flows between services and easy definition of service level properties like timeouts and retries. Security features include end-to-end authentication and secure communication between services. Finally, Istio as a package is self-sustaining, monitoring its own performance and scaling its services based on load. Now that we know about the main features of Istio, we can talk about the architecture. Similarly to the Kubernetes master and node planes, Istio has a data plane and control plane. In the data plane, services called Envoy proxies run in the pods alongside each of our microservices. These proxies intercept all traffic to microservices without any dependency to the microservice code itself. Once the requests are proxied, all incoming data can be manipulated by the master plane. The three main Istio services that will be running on Kubernetes are Pilot, Mixer, and Citadel. Pilot handles service discovery, establishing route rules, and resilience features like retries, timeouts, and circuit breakers. Mixer pulls information from incoming requests to collect telemetry data, and Citadel provides a suite of security features, including identity and credential management. It is likely that within an organization, services will need to exist on several different clusters in different locations. In our configuration of the Istio service mesh, multi-cluster functionality is achieved by installing the full Istio control plane on a main cluster, while having a remote configuration on a secondary cluster. Helm, a Kubernetes package manager, was used to create manifests to deploy this configuration on the remote server. All requests will pass through a single ingress gateway, hosted on the main cluster, but services can communicate with each other and be exposed through the gateway from either of our clusters. This creates a service mesh that spans multiple clusters. As of now, our implementation is running solely on GCP and between clusters running Google Kubernetes Engine. In the future, we are working towards supporting clusters on-premise running Kubernetes in a hybrid cloud solution, as well as supporting Kubernetes running on separate cloud platforms in a multi-cloud solution. In this solution, Apigee will be leveraged for its API management capabilities. It will enable the sharing of APIs with developers that may be part of your organization or external. This is done by packaging APIs into API products, which will control who consumes the APIs, how much they consume them, and what level of access they have. Apigee provides accessible API documentation using an industry-standard Open API specification. Additionally, you can add security to outward-facing APIs using various authorization and authentication frameworks such as OAuth 2.0. Apigee also features a usage analytics module that can provide statistics for your outward-facing APIs. Finally, Apigee provides a monetization structure for the packaged API products that you will be creating. Including Apigee in this solution ensures that your company has the capability to enact a consumer-first API product design. Now, we'll be looking at our implementation of the solution starting with the application front-end. Here we have a login screen, where I will log into our Angular-based front-end application. From here, I'm going to go to the Unified Search feature, which will search for product data from various backends. I'll go ahead and enter an item number into the search bar, and it'll return some item data for us here. Each tab in this data table comes from a different microservice and several different backend applications. Additionally, the regulatory data, environmental data, and metallurgical data are simulating a legacy backend, so the services are residing on a separate cluster. However, all this data is retrieved through a single API call to the gateway of our main cluster. And now I'll switch over to our backend. We can look at some of the backend structures in the Google Cloud Console. Okay, so now we're here on the Cloud Console for the Google Cloud Platform. And we can look at some of the backend architecture that I was talking about previously. So we're looking now at the workloads for our main cluster, Tech API Cluster 1, which has the main Istio installation and has all of the features of Istio. Here we could see the pilot branch of Istio, the policy branch, which is actually a mixer, the telemetry features, as well as the ingress gateway, which is also installed with Istio. Finally, there's also Istio Citadel, which will be responsible for all the security features. So these are all installed onto the service, onto the cluster, as well as all of the different services that we have that you saw being used in our front-end application. So what I'm going to do now is just demo one of the, probably I would argue, the most fundamental feature of Kubernetes, which is the capability to horizontally scale. So now if you see, we're inside a workload, and you can see that it's running on a single pod. This is the pod that is running our microservice right now. Inside this pod is the Istio proxy, as well as the code for the microservice that's running. So what I'm going to do now is, rather than have a single pod, I'm going to scale it up to 3 pods. Through the UI, this can also be done through a Cloud Shell using console commands. So as you can see, it's already created 2 new pods and they're initializing, and if I go ahead and hit refresh, you can see now it's running on 3 pods. So obviously this is going to be one of the core features. In a production environment, we wouldn't be scaling manually like this. We would actually be using this auto scale feature that you see here. But for the demo, I wanted to show you guys the manual scaling feature to show how these pods scale. Next, we'll go ahead and look at our remote configuration. Okay, so over here on our remote cluster here, you can see Tech API Cluster 2. You can see that we have a much lighter installation of Istio. Only 3 components. One is the sidecar injector, which will deploy all of these sidecar proxies, as well as Citadel, which is essential security. The services need to talk to each other through mutual TLS certificates to ensure a secure connection between the services, so that's why Citadel has to be deployed on our remote configuration. Otherwise, you can see we have our 3 services that connect to our legacy backend, and these are on a remote cluster. So now we're looking at a graphical plugin for Istio called Graphna, which can present graphical data for all of the logs that are collected by Istio. That'll provide data on some of your microservices. So things like request volume, success rate for each request, the request duration, so you can check out the latency for some of these requests. And there's a lot of other things that you can monitor just to check on the health of your services. Okay, so a lot was going on under the hood when we made our API call using our front-end application. So I've gone ahead and opened up a Postman, which is a REST web client that is used to make API calls manually, to show you a little bit about our authorization and authentication policies that we've used to secure our API. So as you can see right now, I'm sending a request to our Ingress Gateway's URL with that same product number, and I'm not using any authorization. And if I send this request, then I'm going to get a 401 unauthorized response from the backend service. So what I'm going to have to do in order to be authorized is to go over to this URL, which is a OAuth provider. And Apigee is going to act as our OAuth provider in this scenario. The authorization and authentication framework is OAuth with the client credentials grant type, meaning we're going to be sending the consumer key and the consumer secret along with this request, and it's going to send us a JSON web token back that is going to be used to authorize our API call. So I'll go ahead and send that request, and it sent me a long token, and I'll go ahead and copy that whole token over to our API request and send it as a bearer token. Now you can see it's sending the authorization header, and I can go ahead and send the call again, and now you can see that all of the data has been returned. We've got a status code 200 OK. So this is how we've implemented our authentication and authorization framework using Apigee and the Apigee Istio adapter, and we can use this type of authentication to secure external facing APIs that can be deployed as API products to external devs or consumers of APIs.
Thank you, Evan and Dan, for that excellent demonstration. At this time, I'd like to take just a few brief moments to tell you a little bit about Teqtron and our roadmap going forward regarding hybrid and multi-cloud. As I mentioned at the start of this presentation, we are currently modeling our hybrid and multi-cloud solutions. We are internally validating multiple options and will soon bring recommendations to help companies adapt their digital transformational path. One of those ways that we'll be doing that is through our next release and corresponding webinar. If you or your organization would like the details for that webinar and to sign up for it, please contact us directly at contact@teqtron.com or give us a call at our Center of Excellence, 510-573-2713. Again, that's 510-573-2713. If you feel that a more tailored one-on-one approach is warranted, we are very happy and very excited to build out a POC and corresponding guide for your scope of work. If that is something you'd be interested in, please reach out to us again at contact@teqtron.com or give us a call at our Center of Excellence, 510-573-2713. At this time, that concludes our presentation. From all of us here at Teqtron, thank you very much for your time, and we look forward to hearing from you soon.